So we continue the next section of magnetism, that is section B, electromagnet and its uses. Now, electromagnet. So when I take a soft iron rod and I take some wire and connect it over here, wind it over here, and then connect it to a battery, you will find that this particular iron rod acts as a magnet. The moment I switch the power off, it will be off. मैंने इसको power on किया तो फिर से magnet बन जाएगा. So in this way, I can convert any soft iron piece into a magnet by passing electricity around it. So that is called as an electromagnet. So an electromagnet is a temporary strong magnet made from a piece of soft iron when current flows in the coil wound around it. It is an artificial magnet. An electromagnet is made of in any shape, but usually the two shapes of electromagnet are I-shaped, that is bar magnet, and U-shaped, horseshoe magnet. So for construction of a I-shaped bar magnet, to construct the I-shaped electromagnet, a thin insulated copper wire is wound in form of a solenoid around a straight soft iron bar PQ. The ends of the wire are connected to battery B along with through an ammeter A, a rheostat RH, and a key K, as shown in figure 10.4. So this is what they see, that this is the soft iron, and to the soft iron is a winding of the wire like this. So windings are there, and then this wire is connected to a battery using an ammeter and then a switch and then a battery, and then connected to it is a rheostat. Okay, so this is how it is connected. So maybe you can just change the conditions over here. So what they have done is like this. So they have connected the rheostat here, and they have connected the rheostat to the battery and to the switch. Okay, so we find that the current is going to flow from here like this, and it is going to travel inside like this, and accordingly it is going to come here. It will be seen that there will be a south pole generated here and a north pole generated here. This is also because of the fact that, okay, it is because going to be this way. Okay, the direction, if it is going to be clockwise, if the current is going to travel clockwise, so it is going to travel clockwise over here. So it is clockwise over here. So it is going to travel clockwise. Sorry, it will be like this. Okay, I've seen I'll draw it as per the figure. So as per the figure, this side is coming from inside. So that's why it is. I drew it ulta, that's why. So this is the way the coils are there. So this is going to go back and go round, 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 round. You can see this is clockwise. Because it is clockwise, so there will be south pole. And here, from here, if you see, it is going to be like this. So there will be anti-clockwise from this direction. That's why the north pole. So the point, where the current is going clockwise is going to be the south pole, and where the current is going to be seen as the anti-clockwise will be the north position. So to construct the I-shaped electromagnet, a thin copper sheet, yeah, we already read that. When current is passed through the winding of the solenoid by closing the key K, the NP of the bar becomes the south pole, since current at this phase is clockwise, while NQ at which current is anti-clockwise becomes the north pole. So where it is anti-clockwise, it is north pole, clockwise is the south pole. Thus the bar becomes a magnet. The bar shows the magnetic properties only when an electric current flows through the solenoid, and it loses the magnetic property as soon as the current is switched off. Since soft iron has a low retentivity, that means the amount of retention of the magnetism is less. That's why the soft iron does not become a permanent magnet. It will lose its magnetism instantly as soon as the switches move off. So thus it is a temporary magnet. Such arrangement is commonly used in relays. So relay is a kind of a device which is used for switching on and switching off the system. So automatic system को switch on करने के लिए relays use होता है. Normally used in lifts. Okay. And then another is the construction of U-shaped or horseshoe magnet. To construct a horseshoe magnet, an insulating copper wire is spirally wound on the arms of the U-shaped soft iron core, such that the windings on one arm are seen to be at the end in the opposite sense. In 10.5, windings of arm A from the front, and it is in the clockwise direction. On reaching the upper point, winding starts from the back of the top of the arm Q, and which is in the anti-clockwise direction. So you'll find that when you start drawing it, so it will be this way, that if I have got this kind of a horseshoe thing, so the one which I'm going to connect over here will be starting from like this, and it will be from outside, and it is going to go like this. So it will be going यहाँ से ऐसे जाएगा, तो ऐसे करके winding जाएगा. Okay, the winding goes this way, or okay, so this is how it is going, like this, like this, like this, like this. ऐसे करके ऐसे ऊपर जा रहा है. So it is like this. You can see this is like this. So this is nothing but, what is it? Clockwise. So this is the south pole. Over here, when you bring it over here, you are going to take it in the opposite direction. So that's why it is going to travel this way. So because it's traveling this way, that's why this is the anti-clockwise direction and the north pole over here. So when the current is passed through the windings by closing the key, the end of the arm P becomes the south pole and the end south pole, and the current at that point is clockwise, and end Q becomes the north pole. This is the point P and this is the point Q. Q becomes the south pole and this becomes the north pole, because here it is clockwise and here it is anti-clockwise. The magnetic field in the gap vanishes as soon as the current in the circuit is switched off. Thus, it is a temporary magnet. Such magnets are used in DC motors, AC generators, etc. Note, for sending current in the coil, the source must be a DC source, a battery, with an AC source of a frequency 50 Hz. Although the soft iron core gets magnetized as long as the current is passed, but its polarity or magnetics are as long as the current is passed, but its polarity at the ends change 50 times in each second. So we learned that in the previous chapter, that is electric current, that the current could be either DC source, that is in the form of a battery or a cell, or it could be the AC source, which is the alternating current, which is the mains, where you get the plug point in our houses. अगर plug point से हम लोग ने अगर इसको connect किया, तो यही होगा कि you will not get the north pole and south pole, because continuously 50 times in a second this will become south pole and this will become north pole, and 50 times this will become north pole and this will be south. Because of the alternating current, there will be continuous structure, but at the same time this magnetism will take place. That means it is going to form into a magnet, it is going to attract the magnetic material, but the poles are continuously going to get reversed for in the speed of 50 changes per second. So that's why you are not going to use an AC circuit for producing the electromagnet. Now you can increase, now the main advantage of this particular kind of a system is that you can increase the magnetism of this particular bar magnet or the horseshoe magnet very easily. And that is possible by two ways. First is, the magnetic field of an electromagnet can be increased by the following two ways. First, by increasing the number of turns of the winding in the solenoid. So just to increase the thing, I just increase the windings over here. If I increase the windings over here, automatically the magnetic field increases. And second option is to increase the current through the solenoid. So if I increase the current, यानी resistance अगर मैंने कम कर दिया, I put it over here, so the resistance is least. So if I reduce the resistance, or I increase the battery over here, if I am increasing the current passing through the solenoid, then also the magnetic field will increase. So magnetism can be increased, the electromagnet strength can be increased by first increasing the number of turns, and secondly is by increasing the current. So when we talk about a permanent magnet is a naturally occurring magnet since it is not strong enough and requires the required shape of many purposes. So a strong permanent magnet is made like an electromagnet using steel instead of soft iron. A coil of insulated copper wire is wound around the steel piece, and then current is passed through the coil. Once magnetite does not lose its magnetism easily since steel has more retentivity than the soft iron, so it becomes a permanent magnet. The permanent magnets are used in electric meters, galvanometers, voltmeters, ammeters, and magnetic compass, etc. So instead of electromagnets which are soft iron magnets are the temporary magnets, but we can also make permanent magnets from the by the use of electromagnets. So what we do is that instead of using soft iron core, we use a steel core. So if you make it a steel, then steel has, see, we understood that the electromagnet, in the soft iron does not have that much of retention of the magnetism. So retentivity of the magnetism is very less in case of soft iron, whereas it is very high in case of the steel. And that's why once you are winding it with this copper wire and then you are passing the current, this particular rod will become a permanent magnet. So that's why it can be used as a permanent magnet. So the comparison between electromagnet and permanent magnet: electromagnet made of soft iron, permanent magnet made of steel. Electromagnet, it produces magnetic field so long as current flows through its, and it is produced the temporary magnetic field, whereas permanent, it produces the permanent magnetic field. The magnetic field strength can be changed in electromagnet because increasing the current, winding सब increase करके हम लोग change कर सकते हैं. But permanent क्या एक बार बन गया तो बन गया, उसके बाद उसको कुछ नहीं कर सकते. So the magnetic field strength cannot be changed. Electromagnet, the magnetic field in electromagnet can be very strong, where the magnetic field in permanent magnet is not so strong. The polarity of an electromagnet can be reversed. Now in case of if I just change the polarity here, current flow, instead of passing from here, if it passes from here, automatically this becomes the south and this becomes the north. So I can change the polarity, or we can change the poles, north pole to south pole to north pole in case of electromagnet, but I cannot do it in a permanent magnet because permanent magnet में एक बार वो north south बन गया तो उसको कुछ नहीं कर सकता. The polarity of electromagnet cannot be reversed. The polarity of permanent magnet electromagnet can be reversed, cannot be reversed in a permanent magnet. It can easily be demagnetized by switching off the current. So electromagnet can be easily demagnetized by switching off the current, but here it cannot be easily demagnetized. So that is the difference between electromagnet and permanent magnet. Advantages of electromagnet over permanent magnet, which are almost the same thing as what we see in the differentiation. An electromagnet has the following advantages over a permanent magnet. The electromagnet can produce a strong magnetic field. We studied that because we can increase the current and increase the number of curves. Yeah, so if the windings are increased or the current is increased, we can increase it. So that's why we can have a strong magnetic field available. The strength of the magnetic field of an electromagnet can easily be changed by changing the current or the number of turns in the solenoid. The polarity of the electromagnet can be reversed by reversing the direction of the current in the solenoid. So these are the advantages of the electromagnet over permanent magnet. Now we see some examples or the uses of electromagnets. Electromagnets are mainly used for the following purpose. First, for lifting and transporting heavy iron scrap hurdles, plates, etc., particularly when it is not convenient to take the help of human labor. Electromagnets are used to lift as much as 20,000 kg, okay, to 20 tons, 20,000 kg of iron in a single lift. To unload the object at the desired place, the current in the electromagnet is switched off so that the iron object gets detached. So it's the most easiest manner to separate out the magnetic material from a non-magnetic material. Like for example, you take an electromagnet, you place it in a particular area where there are too many iron pieces and switch it on. So all the iron pieces get attracted to it. You drag it out, so automatically non-magnetic material will be left out. ये पूरा का पूरा लिफ्ट किया, इसको कहीं और लेके गए और उसके बाद उसको रिलीज कर दिया, इट विल फॉल इनसाइड ओवर देयर. Not only that, furnaces वगैरह जहाँ पे temperature is very very high, you cannot allow a person to go and insert the iron material into that furnace. So in that case, electromagnets are most helpful because electromagnet सिर्फ iron pieces लिया, furnace में डाल दिया by just switching off the electromagnet. That's right. That's the second use, that is for loading a furnace with iron. Third, for separating the iron piece from debris of ores where iron exists as impurities, for separating iron from the crushed copper ore in copper mines. So whenever you are using copper mines में iron का जो part है उसको remove करना है, so we are going to use electromagnets over there, place the electromagnet inside and then drag it out. So all the iron pieces will be separated out and the copper will be remained. For removing pieces of iron from wound, so yes, if there is an accident and in the wound there's a deep wound wherein the iron pieces have entered inside the body, then they can use electromagnets to drag that thing inside from outside. In scientific research, to study the magnetic properties of substance in a magnetic field, yeah, scientific researchers. And then finally is in several electrical devices such as electric bell, telegraph, telegrams, electric tram, electric motor, relay, microphone, loudspeakers, etc. Use electromagnet in an electric bell. So that's the last one was the electric devices, electromagnetic devices like the electric bell. And now we are going to see the use of electromagnetism in the electric bell. So that's a very nice kind of explanation. Nice to understand and know that how exactly the electric bell functions. So I'll make a rough figure for this one, so that you get an idea about how it is formed. So what is there is, first of all, there is a gong, and this gong has got a hammer which can hit this particular gong. So this hammer is somewhere here and it is having a strip like this. The strip is connected to another kind of a thing over here, strip over here, which is going to have the wiring connection. So yes, rahega. And then there is you can say a screw sort of thing over here. This is wherein the battery is connected. So the terminals of the battery, so this is one terminal, T1 is connected here, and to the other side from here comes a horseshoe magnet. We are going to have a electromagnet over here. So the electromagnet will be placed inside over here. So that is how it will be. Okay. And then this point over here is connected to the other terminal, T2, that is the connection is going to be the battery and the switch over here. Okay, this is how it is going to work. Now, so what happens, actually what is going to happen is going to be this way, that okay, this is, the current is made to switch on, the current flows from here, it flows here, goes here, goes to this point, goes to this strip, goes to this point, travels inside this particular electromagnet. So it becomes an electromagnet. So once it becomes an electromagnet, this particular strip gets attracted towards over here. So this is going to get attracted and going to be like this, okay? And hence the gong is going to hit by the hammer. The hammer is going to hit the gong. Okay, ये क्या होगा? ये इधर attract हो जाएगा, तो ये hammer gong को मारेगा. Okay, so that is how ting करके आ जाएगा. But what has happened is that when this shifts over here, the contact over here has also got shifted. So this has got shifted, and because of the shifting over here, this gets demagnetized, and because this gets demagnetized, it comes back to its original position. We like this. So ये gong एक बार बजने के बाद वापस इधर आ जाएगा. पर जैसे ही इधर आएगा current again starts flowing, again it becomes a magnet, so again it hits, so again a ting is there. That's why there will be coming continuous ding 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 और करके bell जो बजने लगेगा, because till the time this switch is on. So till the switch is on, the current is going to flow, magnet is formed, attraction यानी current breaks, but यहाँ पे एक बार ting हो गया, current break हुआ यानी demagnetize हुआ, ये फिर से अपनी जगह पे आ गया, signal अपनी जगह पे, यानी this comes back to rest. But when it comes to the original position, again the current flows, again it becomes magnet, so again it hits, and that's how the continuous ringing of the bell takes place in a electric bell. So this is about the functioning of the electric bell. Let's read this out. Construction. An electric bell is shown in figure 10.16. The main parts of the bell are a horseshoe magnet M having a soft iron core. Second is the soft iron armature A, a hammer, a gong, a metallic strip SS, an adjacent screw S, a switch K, and a battery. The armature A is fixed up to the spring strip SS. The hammer H is attached to the upper end of the armature A. When the switch K is not pressed, the strip SS makes contact with the screw S1, and there is a gap between the armature A and the poles of the electromagnet. The coil CC is wound on the two arms of the electromagnet in the opposite direction as shown in the figure 10.16. One end of the coil is connected to the terminal T1 through the strip SS and the screw S dash, while the other end is connected to the terminal T2. A battery is provided in series with the switch across the terminals T1 and T2. So this is what they are given you, the figure, explanation of this figure. This is the gong and this is the hammer. Working. When the electric current is closed by pressing the switch K, the current flows to the coil CC and the core of the electromagnet gets magnetized, and therefore it attracts armature A as shown by the arrow in figure 10.16. Due to movement of the armature A, the hammer H strikes the gong G and bell rings. At the moment when the armature A, due to magnetic attraction, moves towards the electromagnet, the connection between the strip SS and this particular screw breaks, due to which the flow in the current in the coil loses magnetism, stops coils, and consequently the electromagnet loses magnetism. That is, it gets demagnetized and the armature A flies back to its original position due to the spring effect of the strip SS. Now the armature again touches the screw S, resulting in the flow of current in the coil. The electromagnet regains its magnetism and the armature A is again attracted, so the hammer H strikes again. The gong G. This process continues. The process to make and break of the circuit goes on, and the hammer strikes the gong repeatedly, so the bell rings as long as the switch K is kept pressed. Note, if an AC source is used in place of a battery, the core of the electromagnet will get magnetized, but the polarity at its ends will change. Since attraction of the armature does not depend on the polarity of the electromagnet, so the bell will still ring on pressing the switch K. So even if I don't use the battery over here, but I put a AC circuit over here, the mains, that is our plug point over here, still this is working, because here no doubt the north south direction का वो जो है वो लफड़ा होने वाला है, पर उससे फर्क नहीं पड़ेगा, because the attractive property of the magnetism is still going to be there, and due to the attractive property the hammer will get attracted, means the strip is going to get attracted and the hammer is going to hit the gong again and again. So even if it is a AC circuit, the operation of the electric bell will still be the normal without any change. So no doubt there will be magnetized polarization जो है proper नहीं होगा, poles बनेंगे नहीं, but it doesn't matter because we are not having any function of the poles over here. What the function what we are using of the electromagnet is just magnetism. It is just to attract. Okay, there is nothing like to have a particular pole at a particular point. So that's why it is written over here that in an AC source, if an AC source is placed in the place of a battery, the core of the electromatter will get magnetized, but the polarity of its ends will change continuously. Since attraction of armature does not depend on polarity of the, so here the attraction of this thing is not depend on the polarity, so the bell is anyway going to still be ringing when the key K is pressed. So this was the end of the chapter magnetism. There are no numericals in this particular part, no calculations, but very easy chapter. Yeah, so that's the end of magnetism. Thank you.